The odd thing about this, the way the Zumthal named his chapters, chapter 14 was acids and bases, and chapter 15 is acid-base equilibrium. But we've already talked about equilibrium. So I guess you just choose your name and go with it. The chapter 15 is largely focused on buffers. And buffers are exclusively in the domain of equilibrium. So there are two ways to shift an equilibrium: by changing the concentration, right? You can directly change the reactant or product concentrations, right? Or you can indirectly change the reactant product concentration by coupling them with a second reaction. We did that in our lab. We had a couple of reactions that it removed reactants or products. Now we're going to introduce this concept called the common ion effect. In order to shift an equilibrium, if we use the indirect change of reactants or product concentrations, the two reactions must have a common ion. They must have an ion in common between the two in order for the second reaction to affect the first. And that's where we can then apply Le Chatelier's principle. So here we have an acid ionization reaction where hydrocyanic acid and water produce hydronium ions and cyanide. So what would happen if we added sodium cyanide to this solution? What are we actually adding to that solution? I'm going to write it in the abbreviated format. If we add sodium cyanide, what's the common ion? Right there. That's what you're adding. This is a spectator. All right, so we're adding this cyanide ion that increases the concentration here and shifts the reaction to the left. Okay, so what does that mean? If we add this to the solution, what happens to the pH? The hydrogen ion concentration goes down, the pH goes up. All right. So with that concept in mind, what is a buffer? Well, we can talk about buffers in terms of many types of chemistry. It doesn't even have to be chemistry to call it a buffer. But in chemistry, when we talk about an acid-base buffer, we're talking about a solution that resists pH change. When an acid or base is added. So if we have a solution that's in its buffer range and we add a strong acid to it, the pH may drop just a hair, but not much. There's something going on. There's a secondary reaction going on in there that is consuming those hydrogen ions that we're adding with our strong acid. All right. Typically, buffered solutions are a combination of a weak acid and its conjugate base in the proper proportions. And we're going to investigate that, find out what the best proportion is eventually. We can make a buffer solution with acetic acid and acetate ions. So how would you do that? How would you get acetic acid, C2H3O2, and its conjugate base? How would you get those two in solution together? Well, I can think of two ways. One way is just to take some acetic acid and some sodium salt and just put them together. Right? Or you can take this solution and you can titrate it by adding sodium hydroxide until you reach the desired concentration of acetate ions. Either way works. This way is simpler, but the result is the same. Okay, so in ideal conditions, we produce a buffered solution. Now the question is, why is that buffered? Why isn't some other solution buffered? Why can't we say hydrochloric acid and chloride ions? Why isn't that a buffered solution? Okay. I'm going to, let's see. I'm going to take acetic acid and use that as our example. So if you've got acetic acid in solution, C2H3O2 in abbreviated form, and you have some of these and some of these, okay? Let's say we have enough of these and enough of these so that we set up an equilibrium, and now these are available and these are available in significant amounts. All right, what happens if you add acid to this mixture? Right? If you add this to it, what's going to happen? This is a weak acid. This is a strong conjugate base. So if you add hydrogen ions to that solution, what's going to happen? Nobody has a clue. You add hydrogen ions to this solution, right? You're going to combine those with this and drive the reaction back that way. So what does that do for the overall hydrogen ion concentration? It means that it shifts very little. Right? Le Chatelier says we're going to reestablish equilibrium now at a different equilibrium position. But the equilibrium position in this case is going to be very close to the original. Not exactly, but very close. Because of that strong base. All right. All right. What's the next scenario? Right. We're looking for common ions. What happens if you add hydroxyls? Right? If you add hydroxyl to pure water, it's going to shoot the pH straight up. But if you add it to this solution, it's going to combine. This is what? The strong conjugate base of water. So it's going to latch onto those hydrogens, right, and make water. But what's that going to do to the equilibrium? The equilibrium is going to shift this way. Right? It's going to make hydrogen ions to replace the ones that we missed. Not all of them, just enough to reestablish equilibrium. So instead of the pH going sky high, it's only going to drift up a little bit because we've replaced a lot of those hydrogen ions with a shift in equilibrium. Okay, so that's what happens when you add an acid or a base to a buffered solution. Now, can we keep doing this forever? Like keep adding acid to acid, 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 or a base and base and base, just keep adding it, right? What's going to happen? Eventually, with acid, you're going to consume all of that, or most of it. If we add a base, we're going to consume most of this. So there are limits. That's known as the buffer capacity. So the buffer capacity is an extensive property. In other words, it does depend on how much there is. So you can exceed the buffer capacity, and at that point, the pH is going to change rapidly in one direction or the other. All right. So now I mentioned earlier that I was going to show you the shortcut for finding the pH of a solution. This equation that we're going to talk about, the Henderson-Hasselbalch equation, is especially useful when we're discussing and calculating pHs for buffered solutions. How is it developed? Well, Henderson took just the standard equation for an acid ionization and wrote the K value for it. Right there it is. Hydrogen ions times conjugate base divided by unionized acid. And he solved for the hydrogen ion concentration. Right? It says, okay, here's my equation. This is the Henderson equation. It says this way, if I know the Ka for the acid and I know the concentrations at equilibrium for the unionized acid and the conjugate base, then I can calculate the hydrogen ion concentration. Well, that was before Henderson worked before Sorensen came up with his modification to give you pH. When he did that, Hasselbalch took Henderson's equation and applied that transformation, the negative log transformation, to that entire equation. Right? 1908 was when Henderson worked. Sorensen came along a year later, proposed the pH system. And then a few years later, Hasselbalch took that equation and did a negative log transformation for the entire equation. So there's Henderson's equation. We're going to take the negative log of everything in that equation. Right? So remember how logs work. Well, actually, you don't need to know for this one. The negative log of hydrogen ion concentration is what? pH. The negative log of Ka is what? pKa. And we leave the negative log of acid over conjugate base alone because those values are variable. We don't want to mess with that one. So we're going to leave it like it is, except when we get this value, notice we got that negative sign in there. Negative signs have a tendency to get lost in calculations. So we're going to get rid of that negative sign. How do you do that with a log? You invert the quotient. Put the A minus on top and the HA on the bottom. Now the log is positive. That's the Henderson-Hasselbalch equation. If you know the pKa for the weak acid and you know the concentrations of the conjugate base and the acid, you can calculate the pH for that solution. Okay? So notice with this equation, with that equation, if these concentrations are exactly equal to each other, this is X and this is X, what do you get? X divided by X is 1, right? What's the log of 1? Well, it's 10 to the power that gives you 1. So that's equal to 0. So if you have equal concentrations of the conjugate base and the acid, then your pH is going to be equal to your pKa. All right? That's what we're going to do in the lab Thursday. We're going to titrate and find out the point on our titration curve where these two are exactly equal, then the pH that we got for that equality will give us the pKa. And then we just take the anti-log of the negative value of that, and we get the Ka. That's how we're going to calculate the Ka for acetic acid. It's really, really a simple lab. All right. So what's the pH of a buffer solution that has 0.45 molar acetic acid and 0.85 molar sodium acetate? That means the concentration of the conjugate base is 0.85 and 0.45 molar is the acid concentration. The Ka is this value. We just plug those values in and our concentration is 5.02. I mean, our pH is 5.02. We could have gone through and created an ice table with those two concentrations and calculated what the hydrogen ion concentration is, but we don't need to. This is easier. All right, so I'm going to stop there. Okay. So good buffers contain relatively large concentrations of the acid and its conjugate base. Right? That gives them large buffer capacity. Now, at lower concentrations, we can get a buffer, but it just won't be effective for very long because the more acid you add, the more conjugate base you consume. So the actual pH is determined based on this ratio. So if we have a large amount of conjugate base, then the pH is going to be shifted a little higher. If we have a larger amount of acid, the pH is going to be shifted a little lower. What does this look like when we titrate? Right? This would be added base, usually hydroxyls. And this would be the pH. So if you start off with a monoprotic acid, you start off at an acidic pH, and it goes up for a while, and then it levels off. This is your buffer zone right in here. Notice the pH isn't changing. So as we add more and more base, we exceed the buffer capacity, and then it goes like this. That. This point is the equivalence point. That's when the moles of hydrogen ions and the moles of hydroxyl ions are exactly equal. So this volume here, that's volume of equivalence. Right? Where do we, in this graph, do we have exactly equal amounts of conjugate acid and conjugate base? Right here. Right? This is 1/2 equivalence. And that's equivalence divided by 2. Okay. If that's the case, then all we have to do is read the pH here. This is pKa. Okay. So the best place to be in a buffer is where you have exactly equal amounts of conjugate base and acid. All right, I mentioned buffer capacity before. It simply means it's an expression of how much acid, how much acid can be added before you exceed the capacity, or how much base can be added before you exceed the capacity. And the pH starts to change. Large capacity means large concentrations of both of these. They're still 1-to-1 ratio, but large concentrations will give you a larger capacity. All right. This is a quantification of buffer capacity. You don't have to memorize that. I'm just showing you what it looks like. Right. That's a capital beta, Greek beta. delta N is a change in normality of the added acid or base. So that's an expression of how much acid you add or how much base you add in terms of hydrogen ion concentration or hydroxyl ion concentration. And then the denominator is what effect does that have on the pH change? Right. So if you can make this very large, right, you can make that delta N huge with only a little bit of pH change, then you have a large beta or a large buffer capacity. All right. Now, when we talk about normality, right, we didn't define that yet, did we? What does normality mean? I have to assume we didn't. We know what molarity is, right? It's moles per unit volume. And in terms of acids and bases, say acid, for instance, this would be the number of moles of hydrogen ions per unit volume of liter. Okay? Normality is an expression that says, all right, how many moles of hydrogen ions do I actually get from the molarity of the compound? Actually, that's not correct. This is moles of the acid. This is moles of the hydrogen ions per volume liter. So what we're saying is, if you have 1 molar hydrochloric acid, we have one normal hydrochloric acid because it produces 1 per molecule. If we have 1 molar sulfuric acid, that would be 2 normal sulfuric acid, because for every 1 mole of dihydrogen sulfate, you get 2 moles of hydrogen ions. That's what normality means. Okay, when you're designing a buffer, you want a buffer that will give you a pH as close to the pKa of the acid as possible. That would be your best buffer. So choosing your buffer depends upon the pH of the solution you want to maintain. All right, here's these are the definitions I gave you in that diagram. Equivalence point, which is the stoichiometric point for acid and base. And then the half equivalence point is where you've only neutralized or ionized 1/2 of the acid. And this is a titration curve for acetic acid. Right? This is what your titration curve should look like when you finish the lab. You have to draw this titration curve and derive the pKa from it. So it's kind of a manual operation. All right. So we could do a similar titration with a strong acid, but it wouldn't give us a good buffer zone. We could do a similar titration with sodium hydroxide and add acid. In that case, we just invert the titration curve. Okay, very often when we're doing titrations, acids and base titrations, it's useful to determine what type of problem it is. Because sometimes it's more effective and quicker to solve the problem if you treat the problem first as stoichiometry. In other words, let the reaction run to completion, then take the results and work it as an equilibrium problem. I'm going to give you an example here in a second, if I don't run out of time. So in this problem, we mix 0.1 mole of hydrogen cyanide with its Ka and 0.04 moles of sodium hydroxide in 1 liter. What are the major species? Well, hydrogen cyanide is a weak acid, so it's going to be one of the major species. The others are sodium, hydroxide, and water. So we have 4 species here that are considered major. All right. What are the possible reactions? Well, of course, water, right? Water it's a amphoteric nature. We could say HCN and water, right? That's a possibility. HCN and hydroxyl. Yeah, that could work. Wait a minute. Was hydroxyl one of the major species? Yes, it was. Sorry. So hydroxyl is a major species. That could be a competing reaction. Sodium and hydroxide won't happen. Sodium and water won't happen. Cross those out. So now we have to compare those top 3. Right? How do we decide which reaction controls the pH? Well, if we take the one where hydrogen cyanide reacts with hydroxyl, we end up with hydrogen cyanide, cyanide ion, water, and sodium ions. We'll see the sodium. Sodiums are spectators. So, in order to determine which reaction is dominant, actually, in this case, we're going to let the reaction go to completion. Well, actually, we're not going to do that. These are just hypothetical questions. So which one would we go with the reaction to completion? We would take that last one. Hydrogen cyanide plus hydroxyls yields cyanide ions and water. That gives us a cyanide ion concentration and what's left over, right? So that gives us cyanide ions, hydrogen cyanide concentration also, and then we go to the second equation for our equilibrium. All right. So we're going to switch gears on you, sorry. Now we're going to say, what's the pH of this solution? 0.2 moles of acetic acid are added to 1 liter of aqueous solution and 0.03 moles of sodium hydroxide also in that solution. Okay. These are the major species. All right, we cross out the ridiculous ones, and we let the reaction of acetic acid and hydroxyls go to completion right here. And that gives us, actually, that's not equilibrium. That gives us 0.17 because we're reacting all of the hydroxyls with our acid, using them up. Right? So that leaves us with 0.17 molar acid and 0.03 molar acetate ion. Now we can go to the equilibrium equation with acetic acid dissociation in water, and we can do the calculation and find out that the pH is 3.99. Well, if we know what those concentrations are from the previous slide, we can use the Henderson-Hasselbalch too. So if we do that, we get the same value, 3.99. That's easier, I think. All we have to do is find out what are those concentrations, 0.17 and 0.03. So if you let the reaction go stoichiometrically to completion, that gives you your acid and your conjugate base concentration. Then use Henderson-Hasselbalch, and you can calculate the pH from that. Saves you a lot of time and work. All right, here's another example. Let's see. Let the reaction go to completion first, right? And then take those values, put them in Henderson-Hasselbalch, and find the pH, right? I'm running out of time, so I'm kind of skipping things. What if we have 100 milliliters of 0.1 molar solution of ammonia which has a KB value, which has already been calculated for us, and then 50 milliliters of 0.1 molar ammonium chloride. What's the pH of that solution? Well, what we started out with, and then what we end up with at equilibrium, right? We continue to solve the equation, and at equilibrium, we have to calculate the KB because we're talking about a KB react. Actually, we have to talk, no, cancel that. We're given KB, we need Ka because Henderson-Hasselbalch works only with Ka. So you take the KB, convert to Ka, and well, this is actually, they're doing this one the long way. First time is 9.56, so doing it the long way. Okay, now we're going to do it using Henderson-Hasselbalch. So at equilibrium, we have these concentrations, but now we need the Ka. So we calculate the Ka and the pKa, obviously, and then plug it into Henderson-Hasselbalch with our concentrations, and we get the same value. It's a lot quicker that way. Let's see. I've got you, what, 11:15? Okay. A few more minutes. I think I still need to talk about indicators. Let's see. What's the pH of a solution by mixing? So this KB value. All right. So before the reaction, this is a better approach rather than ICE table for the stoichiometry. Before the reaction are the concentrations given. Then after the reaction, you have this. Then you have to calculate the concentrations because we were given absolute amounts. Then you calculate the concentrations, plug them into Henderson-Hasselbalch, and you get pH. All right, let's see. This is an example of calculating the pH at the equivalence point. So if you have these concentrations, 100 milliliters of 0.1 molar acetic acid with that Ka, and it's titrated with 0.1 molar sodium hydroxide, then we're saying what happens at the equivalence point is all of the acid is gone. And we end up with 0.05 molar acetate ion. Now we take the acetate ion and react it with water in an equilibrium situation. All right, so we're starting off with 0.05 molar acetate now at the equivalence point. And we need we're going to do this without Henderson-Hasselbalch. So we calculate the KB, and then we use the expression for KB and determine what is the POH, and then determine the pH is 8.72. So that acetic acid will titrate at equivalence to a pH of 8.72. Now, why is that important? Acetic acid, HC2H3O2, at equivalence with sodium hydroxide equals pH 8.72. Why would that be important? It's different for each acid in this example based upon their Kas. Right? The higher the Ka, the higher the pH of equivalence. So our Ka for acetic acid is around 10 to the minus 5, which would be right in this region here. It's kind of hard to see that K. But it would be right about in, actually, no, 10.6. It would be closer to 10 to minus 6, so it would be right up in here. Okay. The reason you want to know that is, and I'm going to skip these and come back to them, is because of indicators. If you want to titrate to equivalence to determine the concentration of your acid using a base, which we did in the first semester, Then you need an indicator, and we use phenolphthalein. Phenolphthalein changes color between 8 and 10. Right? So it changes color where you reach equivalence. So that pH range for our indicator is ideal for this titration. Right? That way, you can do 100 of those titrations in a day, easy. All you have to do is titrate to the color change, rather than drawing a curve for each one. So if you know this pH, then you can determine what's my best indicator, because this pH may be different for a different acid, right? It could change, it could reach equivalence at 5, or it could reach equivalence at 10.5, and you need a different indicator. All right, let me go back. When we have polyprotic acids, we get a titration like this, where I mentioned earlier, as the acid dissociates, or we titrate it with a base, you lose 1 proton at a time. So this first one here is where you lose the first proton, and there's the equivalence point for the first proton of H3PO4. The second proton is lost. Where is my cursor? It's around this. There it is. The second one occurs here. And the third equivalence point is a little more difficult to reach, but it's right there. What we have is a weak acid, H3PO4, that gives us the opportunity for 3 different buffer zones. Right? The first buffer zone is slightly above 2. So if you take your phosphoric acid and titrate it with base until you reach a pH of about 2.5 or 2.2, then you're right in the middle of its first buffer zone. If you want to use phosphate buffer and you go to pH of about 7.2 or 3, continue titrating with your base until you get to that pH. Now you've got a different pH buffer, and it'll buffer in that range. Or you can go up to 12.3. So that's why in the biological sciences, many of the buffers are phosphate-based, because they give you the opportunity to pick one of 3 different buffer zones. All right. So an indicator, we have an equivalence point for an acid-base titration, which is exactly stoichiometric. Where the hydrogen ion concentration is equal to the hydroxyl ion concentration in the titration. But we'd rather have the ability to do lots of these titrations quickly. So we search for an endpoint. The endpoint is where the color changes. And if you choose your indicator correctly, it will color change very close to the stoichiometric point or the equivalence point. That's the difference between equivalence point and endpoint. Now, the other thing to realize is that indicators are weak acids. That means the indicator undergoes its titration also. At the same time as the main titration, the indicator is undergoing that same titration. But it doesn't take up a lot of the acid or base that you're adding, because in very small quantities, it gives you that color change. So here's our example. HIN is the indicator with the hydrogen still attached. It's a weak acid. So it would be in equilibrium with hydrogen ions and conjugate base indicator. Well, for phenolphthalein, when you have the conjugate base indicator in excess of about 10 times as much IN minus as HIN, then you get the pink color. Whereas if the HIN is about 10 times the IN minus, you get the colorless. And the Ka for this reaction is 3.9 times 10 to the minus 9, or 9.4. The pKa for this indicator is 9.4, very close to the pH of equivalence when we titrate acetic acid. That's what you're looking for. The pKa of your indicator needs to be close to the pH of equivalence of the acid you're titrating. Right. You don't have to memorize those structures, but that just shows you that this phenolphthalein structure is changing by losing a proton. And when it does, it changes its structure in such a way that it absorbs light differently. That's what we're seeing with the pink color. All right. And that's typical for all indicators. They will change when they lose that proton. Okay. Now we have to interject some physiology. The human eye can detect a change of color if the difference between the concentrations of one side of the reaction and the other side is about 10 to 1. So plus 10 times difference, and we're talking about the ratio of the here to there, right? Conjugate base divided by the acid. Right? If this ratio is 1 to 10, we see one color, and if it's 10 to 1, we see the other color. So the range here is plus 1 pH this way and minus 1 pH this way. So pKa plus or minus 1 pH unit gives you the range, roughly, the range of your indicator. So if we have, what was it on the previous page? 9.4. So 9.4 plus 1 would be 10.4, minus 1 would be 8.4. That's roughly the range of pH where you see the color change. And since you're in that part of the graph where it's very steep, the slope is high, then just a little bit of added base will exceed that range. No problem. Gotta go. Okay. I'm just about finished. The nice thing about this chart is that you don't have to go to all this trouble. You say, all right, what's the pH when my titration is at equivalence? And then you look here and say, okay, if it's pH of, say, 5, we would come down to maybe methyl red. It would change from red to yellow. That's the way you read that graph. And that makes it a lot easier if you're trying to design a titration.